All right. Hey, Kayvon. Hey, Tomislav. Hey, Joshi.
Good morning.
Hello. Hi, everybody.
So I guess today I didn't really have a whole ton of time to think about an agenda, just like a few hours last night and today when I was thinking about and struggling with the ladle paper. I feel like there are still quite a few pieces missing for me in ladle as it's fully presented to be able to give like a really great top to bottom presentation. So I'm hoping today to just sort of like highlight some of the aspects that I think are important and that I think have helped drive some of my understanding. And hopefully we can just open up the discussion that way. And then also, I guess I'm hoping that Daniel or Christian might pop on later because I think that they would be valuable resources. But yeah, so we can just get started by talking about Greg's lecture last week. So or on Monday. And so as I understood it, he gave us sort of like a mini baby version of Ladle where we're only talking about the sets of terms in a language. We're only talking about the programs in RoCalc or in another language presented in a calculus style presentation that can be expressed. And we're not necessarily yet concerned with how those programs reduce and how those programs actually execute. But even so, just talking about this sort of simple term language and expressed in this way, we can get a pretty decent idea of the mechanics behind logic as a distributive law or the Ladle algorithm. Let me share. So just as like a little piece of motivation, I thought there's some pretty cool examples here. I've just pulled up the Ladle paper, which if you guys want to pull that up as well and follow along, I've just pasted a link. And so eventually what we want to be able to do is write statements sort of like the one up top here. And what this highlighted statement says is that this will pick out all of your processes that will always be able to handle another. So you can think of this as like a type, a behavioral type. Oh no, did my recording just stop? No, okay. I don't know what happened there.
Jake, I don't see you said something about a highlighted one. I don't see
Yeah.
any highlighting. I don't know if other people can see that.
Oh, can you see my screen highlighted at
No.
all? No? Okay. Let me, yeah, I've continually had problems with, let's try to do the whole desktop. All right, now?
It's just black.
Can you see? It's just black. Okay. All right. All right. Well, so you see the problem that the line that says mu x dot receive top xx in par with top, that line there.
It's just black. Or at least I only see black right now.
Me too. Me too.
Oh, there we go. We got
Yeah.
screen now.
Okay. Yeah, I don't know. My connection here in this new place might not be as good as my old connection. So
It looks good now. Yeah, we see the
okay.
mu x receive line.
All right. So this is that statement that I was talking about that says that this is sort of a type declaration that says programs which satisfy this type, the lay definition is that they will always be able to handle another message. So still sort of working through some of the details here, but you can think of this, just ignore the mu-x dot for now. And what this is saying is that when we have a receive of, and then this, if receive on any name, some process, then that process will decompose. So this is the receive, the first thing before the comma is the name that we're receiving on, or the collection of names that we can receive on. And the thing after the comma is the continuation. So this is saying that when we receive on any name, our continuation, and then this arrow here says like decomposes to something of this type, yeah, our continuation is something of the same type that we've defined here. So this large X, this is a recursive definition for a type. And so this mu X out front here gives us a fixed point. This is saying it's picking out the largest fixed point for this recursive definition. And so whenever we're referencing X, we're referencing, it's sort of a self-reference. So this means that we have, these are all the programs that have a receive in parallel with something else, such that whenever the receive executes, it also is of the form receive something in parallel with anything else. So that means that we're always able to handle another message. There's always going to be something receiving on some name. Is that clear? And yeah, I know that the probably the fixed point operator thing and then this like arrow notation probably isn't too clear because it's not quite clear to me yet. But the general outline of like what the statement is setting out to do, and the fact that, you know, we sort of have our normal row calculus terms, but instead of like, you know, a receive is usually parametric on a single name and then a process. Now inside of those holes where we usually just put a single name or process, what we're doing is we're putting collections of things in those places. So the collection of things we have here is just the collection of all names, which this is a little bit ugly. I think there should probably be a quote around that T. But anyways, the idea is that we have the collection of all names, and we have that the continuation is the continuation can be anything from that collection of names, or the name that we're listening on can be anything in the total collection of names that exist in our language. And our continuation is anything that has the form that we are describing here, which has at least one receive on a name in it. Sorry, I kind of jumbled that definition a bit, but is that, what questions do you have here? Or is this decently understandable?
So this is Kevin. Isn't this kind of what we're doing with Rowlang today?
So sort of. But we have this new idea. So you can't write down any Rowlang process that says, oh, okay. So are you saying, is this like the receiving multiple things at once?
Right. Receiving multiple things at once.
No. So this is not like that at all. So what this is saying is, this is a single receive. So a receive of only one thing. It's just that it can be picked out from, how do I say this?
Can I add to what
Yeah.
So we spent quite a bit of time going through whole and context and how a process can move through context.
Uh-huh.
Is this is this somewhat related to that? That
It is.
okay.
Not so much about the movement through the context, but it is definitely related to the concept of a process with a hole in it. So if you think of the process that I have receive whole from whole, and then generally when we've talked about like locations and we've talked about filling those holes, we've talked about filling those holes with a singular process. In this case, though, we're saying what can fill that hole is one of anything in this set collection that we have.
I see. Now, we also talked about that it's no longer just a name, it's a pair of name and context, right? Does that fit in here as well?
I don't think it does. No.
So what kind of things could go in there other than processes?
In those holes?
Yeah.
Any sort of collection type that you have of processes.
Okay, so if I just have like an ordered list of processes.
Uh-huh.
Okay.
And so yeah. Mm-hmm.
But not some collection of processes.
Exactly. Yeah. Although, yeah, so this really should have quotes around it, if I'm reading this correctly. I guess the quotes are probably implied. But okay, we'll break this down a little bit. I think we're still sort of in the motivation phase. So here's another statement. And this statement says that my process can only receive messages from the set of names, quote, phi, which, so from the set of names gotten from the quoted process, sorry. What's the best way? I'm just going to call that set of names phi. So basically we have a set of names and we want to write a type that says our process can only receive messages from that set of names. And so here is that statement. So, and breaking this down a little bit further, again, we have this recursive definition type thing. So we're going to use that definition in our definition that we have. And what we're saying is that we have in parallel some receives on phi, on something in this set of names. And whenever we do, we decompose to either something of the same form, which we're still going through, or the stopped process in parallel with the set of all processes. So this is the set of all processes that that are not listening, or that are listening on some set of names that are not phi, and then we're removing them from the set of all processes to say, to say that we can have things in parallel that are not receiving on phi, and then this is the same thing here. So, but I guess let's go into like what these knots and stuff actually mean. This is just motivation. We can create these one-line statements that mean some pretty powerful things in terms of the behavior of a program. So popping up to here then, so say we have a language X, which it's a monad These are, or a monoid, I guess, or monad, yeah. But its generators are A, B, C, and D. So these are terms in our language, and we can compose any number of terms together to get a new term. So in Rolang, this would be, if we had only 4 different processes, A, B, C, and D, and then we could par them together to get, B par D or whatever. And what LADL allows us to do is take, I guess these ors really aren't defined yet, are they? Yeah, it's probably this table is better to look at first. Yeah, sorry, I forget what I said up there. So Greg wrote down this table, and this table shows us how we get from a term that's built across collections. And so those terms are examples of the terms that I showed you below, just before, and how we translate those into a collection of terms. So in this case, for our collection type, we're using the set type. But as I said earlier, right, we can use the list, we can use other different types of collections. So I'm afraid I'm losing some high-level context here, but the things inside of these double brackets, and I guess, are you guys seeing my highlighting now?
Yeah.
Okay, good. The things inside of here are describing a language, a new language that we are using to write down the statements that we were just looking at. So that language contains the statement true. It contains the statement false. It contains the statement that is anding or oring 2 statements together, or anding 2 statements together. It contains the negation of the statement, and it contains like sentences, I guess. And we can also talk about, we can also use our high-level language construction terms in these statements. So just like we were able to use the par operator in our language, we can, in our language for logical statements, and what that was interpreted as is a sort of picking something from a collection of a bag of things on either side of the par operator. So the par operator just becomes like the to-hold context of the par operator running 2 things in parallel of 2 different types here, which I think that'll become more clear once we talk about like how these statements are actually represented. So for the true statement, the meaning of the true statement is really our whole language. So when we say that, I guess something is of the type true, we're saying that like any language, any sentence, any program in our language is going to satisfy that type. Or if the type is false here, then no program is going to satisfy that. Now, if we have the logical statement or of 2 of these, so of two of these different statements, then what we're going to take is we're going to take the union of the two sets that are produced. So you can see here what this means is that if we have true, which is true or false, say is our type, that will equal the meaning of true, which is going to be the set of all processes, union with the meaning of false, which is the empty set. So if you union something with the empty set, you just get the set that you were unioning. So we see that true or false is equal to true, right? Which is understandable to us, right? As something.
Yeah, definitely. That one's graspable.
Cool. And then if we are saying that we're negating a statement that we're taking, that means we're taking the set of all things in our language and just subtracting all of the elements out of that set that were the original sort of meaning that we were talking about. I guess rewinding for a second here. So when we're talking about, Greg gave this little sort of motivation at the beginning that when we're talking about bisimulation, what we're doing is we're saying that we have these properties that hold true for our programs, and these properties continue to hold true if these properties continue to hold true in our reductions of our programs, or when they continue to hold true in program A, they continue to hold true in program B. And so how do we talk about these properties? We can talk about these properties as the set of all elements that satisfy those properties. So say my language was like apple, fire truck, banana, and then we wanted to talk about in that language the property of red objects. We could say that the property red objects, we're defining that as, or we talk about that property within our language as the set of fire truck and apple, but not banana. So yeah, yeah.
So do we define the property as basically the collection of all the things that have that property?
Exactly.
Okay.
Yeah. So that's what we're doing here. So the property that is the identity element property is just the identity element in our language, or the set of all things that are structurally congruent to the identity element in our language. So the identity element dot the identity element for our monoid, the binary operation of the identity element with itself is still like has the meaning of the identity element. So all those things are in the set. Yeah.
So, okay, so I've got a question here for just for the field, for everybody. There's the line, the third one down in the left column that it's a not, right? I was thinking of it, like I kind of latched on when we were doing the Boolean example where we defined true as, I guess true is like the set of all of the elements. Is that the idea up in the top? Okay, so let's say we have some A here that's just like a couple, you know, it's not all of them, it's not none of them, it's some, you know, interesting subset. Like we've got three of the elements in A. So then when I do not A, according to that third line, it looks like the result is all of the elements except for the ones that were in A, which is still some of them. So is that Like, is that telling me that not true is still true?
No, so not true. So what we would say is that we would take the set of all elements in our language, that's what that monx says, and we're going to subtract everything in true, which true is the set of all elements in our language. So the set of all elements minus the set of all elements is going to be the set of no elements, which is equal to false.
Okay, got it. So true means all of them, false means none of them. Anything in between, like that A I described, that some of them, that's not true, and it's also not false. It's just a different thing.
Yeah, that's a type.
Oh, got it. Okay.
Right,
okay.
because it's describing a collection of elements. So you have just described, right, that property. So
oh, sure.
If it's something that's in between, it's a type. It's a property.
Okay, got it.
And so if we have, something is of property A or of property B, the thing satisfying that is all of the elements in A and all of the elements of B satisfy that. Or if something needs to have the properties A and B together, then that's going to be the what is that called? The overlapping elements of the sets.
Yeah, got it. Okay. How about that very last line in the right column? Actually, yeah.
Yeah. So that's saying that our generators. So this is the language that we're talking about here is the language of the monad. We're not talking about the language of row calculus. We're talking about a very simple language. And so in the language of the monad, we have the identity element, and then we have the generator objects. So this is saying that that we can write, something of the form x in big X, and what that picks out for us is the set of all generator elements, or generator elements dot the identity element, however many times.
Okay.
So, so one of the things that is a monad, or we can think of as a monad, is our is under multiplication our natural numbers, where all of our natural numbers are defined by the generator set of primes or some multiplicative combination of primes. And so we can think of this as a definition for a prime number in our language here. So this picks out the set of all prime numbers, because we're saying that and that we have it's a prime number is not the identity. So we're saying like not E is the first thing in our language, in our statement here, and we're anding it here with something that I guess we haven't talked about this line yet, but we're anding it with the statement that is the set of all things in our language construction that are built from we're removing the set of all things. So it's a not here, so we're removing all of the elements in our language that are built from two different numbers multiplied together, such that neither one of those elements is the identity. So right, because 7 is 1 times 7, but just because it's made up of two numbers doesn't mean it's not a prime, because we can't have, but 7, there aren't any other two numbers that aren't 1 that you can multiply to get 7. So what questions or comments do we have there? I have a feeling like we're going to be probably coming back to this once I get a better understanding of how to build it up. I feel like I'm sort of skipping around quite a bit to the places where I feel like I have some understanding, but because I don't have a lot of stuff sort of like before or after, it's pretty weak in terms of my explaining power. Yeah.
Yeah, that's okay, man. The selective guided tour is still helpful to me. I wonder, does anyone know anything? There's a bigger table up on page 14, I guess, where it lists sorts as N and P for names and processes, and then term constructors. I wondered if we could talk about that, or if anybody. I want to talk about it, but I don't feel like I have a lot to contribute to the conversation. I want to leech off of all of your understanding.
So page.
It was. Hold the phone. Actually, it's under section 10.1. It's the first like big table. I think it's lower than. Oh, that looked similar. Yeah, that was a similar table. We could start with that littler one, maybe. Yeah. There was that one, and then there's
the one. You're talking about this one?
Yeah, I was actually talking about a bigger one than that, but it's a identical kind of table. It's got sorts, term constructors, equations. So this littler one might be even a better place to start, I guess.
Yeah. So I think that this is actually probably this is the presentation of the Levier theory of a monoid right here. This whole thing is, which that's what Daniel was leading us through, which I see that Daniel is on now. I know Christian is as well. So Christian, you got to hear my butchered understanding of LADL so far.
No. Yeah, I can help.
Cool. Yeah, do you have any comments on the stuff I was talking about today, or any sort of ways to explain some of the stuff that I was going through that you think might be of use?
Well, it's not easy to jump into without a background in category theory.
Right.
Sorry, I just joined a few minutes ago.
Oh yeah, no problem.
But yeah, so have y'all gone through the theory of a monoid?
No, so I guess we started that last week. Daniel did, which are you able to jump off from where you left off last week? Is Daniel on?
I don't think he's on the call.
Okay, cool. Yeah, so we didn't get all the way through it. So the way that I was talking about this stuff is sort of from a high level, mostly looking at some statements in our logical language that we're constructing, and then talking about sort of this presentation here where we're using where we're giving how to construct the language for our logical terms, and what their meaning is in terms of when you bring them down into sets, and using that as our collection.
So did you go over why this distributive law from a term of collections to a collection of terms means like computing out the results of a formula?
No, I did not. Is that something that you want to go take over for me? But I'd imagine we'd probably start with this here, this paragraph.
I think that kind of solidifies the motivation.
Yeah.
So when we see that formula, like A or B times D times C or D, intuitively we know exactly what that means, and what it's asking for is everything that fits that formula. And so right below, that's the answer, because you have A times C, A times D, B times D times C and B times D times D. And so the first formula is a term of collections. So the way that we built up that formula was literally by kind of alternating between one of the monads that correspond into the theory of a monoid, and that's the multiplication. So like the innermost parentheses, you're literally like composing the theory of a monoid by kind of creating that symbol in that theory of a monoid. And then you go out and you alternate it with composing it with the monad for the Boolean algebra, which if we haven't talked about that yet, it's have you mentioned it?
Not in those words.
So it's like if you have some set of things and you take the power set, which is the set of all subsets, it kind of like spreads out your set into this big lattice, and you just have unions and intersections and complements. So it's the usual Venn diagram stuff, but it's just like everything that you could do with all of the subsets of your set. And so here that we're just ORing. I think the theory might be up a little bit.
Yeah, but that's what we're doing here, right? When we're saying that when we're saying A or B is the union of the two sets.
Mm-hmm. But yeah, so basically it's called a distributive law because you're kind of distributing the terms over the collections. It's kind of clearer with other examples, but the point is like basically verifying that this morphism from TC, terms of collections, to CT, collections of terms, like verifying that it's nice or so-called natural, corresponds to verifying that the computation happens perfectly, basically. And any slight change you make to the formula corresponds to the exact right change to the computation results. So that's the basic motivation for LADL. And it gives you this powerful query language with which, as we've seen in the Rolang, you can make these formulas that are like scanning the whole web for everything that fits that formula. So it's potentially very powerful.
So Christian, you used the word natural a second ago. Is that the same natural from the phrase natural transformation?
Yes.
Can you remind me what that means again?
So it's the right kind of morphism between two functors. So functors are like functions, except they also map morphisms and categories, right?
Yeah, so the functors, they map the objects and the morphisms, right?
Mm-hmm.
Okay.
So if you have two functors in parallel, so you have F and G both going from a category A to a category B. Mm-hmm. You can picture the image of F as this big like subcategory inside of B, with a bunch of objects and arrows. And similarly, you can think of the image of G as some big subcategory in B. And a natural transformation paints the image of F onto the image of G, such that all the squares commute. Mm. So every time you had a morphism in the image of A, its endpoints like get these new arrows that are like the components of the natural transformations, and they paint it down onto some arrow that is in the image of G, such that that square commutes.
Yeah, got it. Okay, thanks for the reminder.
Yeah. So that corresponds to being natural is really important because it corresponds to every little change you make to the input corresponds to a correct change in the output. So yeah, and that next page is you start out with this distributive law, that's the delta there. And then from that, you can build up this interpretation, natural transformation from formulas to, and what they're doing there is that they should have gone into more detail, but basically, instead of always having to alternate between terms and collections, they allow for either one. But yeah, that's the basic idea.
Cool. Yeah, so Christian, one of the places where I get lost is, I mean, I think this is mostly because I'm not understanding, you know, what the two category definition of row calculus or computational calculus looks like.
Mm-hmm.
So I know that we have all of the, when we're talking about the one category, we're talking about that's sort of the category that exists of all the terms of our language. But somehow to get these rewrites and how these terms sort of reduce and decompose, we add another category. But is one of our categories still the collection of terms in our language, and then our other category somehow holds the rewrites, or what does that look like?
No, so it's still, one is still terms, and then the other is collections. Except now both also have a notion of rewrite. So like we call one of them the theory of the term calculus, but they're both still formal languages that have terms in them. You have a theory of a collection, and you can still build up like terms with or and stuff. So yeah, now we're just adding this one more dimension, where before, when you represent a formal language in category theory, the objects are types. You don't start out with terms immediately. So the morphisms are actually the terms.
Mm-hmm.
So like we were talking about the past couple weeks, like Leverrier theories, they're generated by powers of one object, and then morphisms from t to the n back down to t, if that's the generating object, is some n-ary operation that's going to take in things and give you back one thing. So you can think of that as a term with n free variables. So that's going to take in things. And then the point is, since the terms are the morphisms, then that's why we're going to add these two morphisms, these arrows between arrows, that correspond to rewriting one term into another. So could you go down a little bit?
Yeah.
Yeah, so here, before associativity, the fact that you could like re-parenthesize things was just an equality, but now it's this actual, this two morphism. So you can think of it similarly like kind of like a natural transformation, like we were just talking about, is an example of a two morphism. But yeah, so it's the same theory, except now the point is that it's keeping track of the work necessary to, you know, re-parenthesize things or to do the left and right unit laws. So that's the point, is that we want to equip these theories with knowledge of the actual work it takes to be rewriting these terms. Are there questions about that?
Yeah, I feel like I need to understand sort of more basically the Levier theory of the monoid and the Levier theory of just our language without rewrites before I am going to understand this. But I think from a high level, at least for me, that makes sense.
Okay. Any other questions?
Jake?
Yeah.
I think the two morphisms between processes, it's not clear actually. Can there be a morphism between two processes? I'm absolutely alien to this paper right now. I know I have some background to Levier theory. I haven't looked into this logic as distributive law yet, but just out of my ignorance, I'm wondering if there is any. What would be the morphism between two processes that maybe are running just agnostically? They don't have anything to each other, yet they exist in the program.
Yeah, so I don't know. So what Christian was saying, if I was hearing him correctly, is that our terms themselves are morphisms. So do we have morphisms between morphisms here? Is that what we're looking at?
Yeah, so same for the row calculus. These morphisms between processes are going to be rewrites. So the basic rule is the COM rule, that the communication is a two morphism, where on the left side is some process, which is actually a term in the theory of the row language. And then, yeah, the COM rule is a two morphism that reduces it a little bit.
Okay, so where that line on the left column says S squared to S, that's saying like two processes come in, they COM, and then we're left with a rewritten single process afterwards.
Well, this one is just the theory of a monoid, but the thing about the row calculus is that the theory is more complicated because you have to distinguish between names and processes. So this is a one-sorted theory where the elements of the monoid are the only kind of thing. But in the row calculus, you have to keep track of how you build up these terms in this subtle way.
But if we were looking at the monoid that's specified between the par operator rolling processes and dot being the running them in parallel, then I think, yeah, what you said is true, Josh.
Yeah.
Right? Yeah.
Yeah.
Would you mind going down to the row calculus?
Yeah.
Yeah, so now we have to do sorts.
P squared to P about halfway down is the one I was just describing, probably.
Exactly.
Yeah.
So what's the one, so let's just, can you mind if I just grab another one to try to wrap my head around this? What's the one right below that mean, where we go from 1 to P? What is 1 the stopped process?
So if everything's like a power of P, then 1 means P to the 0. And these are the null area operations, which are, you can think of as constants. So since we build up everything from the null process, it's kind of the only constant along with COM.
And this COM is a little bit different than this isn't really the COM rule. This is the, when Greg was talking about the communication catalyst needed, so you actually need like 3 things in parallel in order to reduce, that's what this COM is.
Hmm.
And then he was using this COM and special properties of it to do the row calculus with spatial considerations. Which is how those were related, but
what's the P star on that send line? It has n cross P star.
So that's a symbol for the, I think it's called the clean star, and it just means 1 or P squared or P cubed or P fourth, because it can take in as many processes as you want.
Okay, got it.
it can take in, it's only one process, but it's a process that is constructed from many parts or can be constructed from many parts. Is that what it's saying? Because when we're
Yes,
trying to,
I think so.
Yeah, I was thinking of that as like sending, maybe so the n is the name we're going to send on, right? And then P star is maybe like a bunch of processes parred together. But yeah, once you par them together, they're just a single process then, right?
Well, it means I think it means or. So I think it can't you send can you not send on multiple processes?
not in the usual, you can't usually send okay, so yeah, so in like row lang, right, you can send multiple processes to a name. So that's like the multi-arity send and the multi-arity receive, I think, is actually what is being talked about here.
Okay.
So this is yeah, we haven't really seen that in row calculus, but we've seen that in row lang. So this is closer to row lang than row calc in that way.
Is it like in Milner's paper that we started out with like months ago, they moved from the monadic to the polyadic PyCalc? Is that kind of similar here?
Yeah, yep. It is. So right in Rolang, right, you can say that like send Q comma P on X, and then a receive that only is expecting to receive two things will match with that. That's what this is doing. It's saying here.
Yeah, I got it.
Yeah, but I think in Rolang we also have the opportunity to send nothing, no data.
Well, I actually didn't know that. What would be an application there? Just a send to like call it, I don't know, to make it
so like
happen somewhere else?
Right. So if you're doing like a function call and you want to send back like an acknowledgement that you've gotten the message, so that because it's asynchronous, so that your sending process can continue, then you don't really care about what that message is. All you care about is that like a message was sent.
Yeah, got it.
Okay. Yeah. Any other questions or comments? Otherwise, we'll pick this up again next week. See where Greg goes, and then see where I go and where my understanding comes into play. And then, but otherwise, I'm hoping maybe Daniel will be back and we'll be able to continue to guide us through the Levere theory of a monoid, and we can sort of build up from there. If not, I'll maybe try to do that, or maybe Christian would want to volunteer to do that. You would?
Sure.
That'd be awesome. And then in the meantime, did find where is the sorry, let me pull up the link here. So I found that AS has been running this summer an applied category theory course. And it's great. And I will, yeah. And it goes through a free textbook written by a couple of MIT professors, 7 Sketches in Compositionality, which is sort of like trying to introduce applied category theory to everyone. And then there's a forum and stuff that you can register for. It's pretty cool. So I'm hoping to go through that to sort of increase my category theory understanding.
There's exercises too. That's great.
Yep. So all of the exercises there's like exercises that are presented in the book with people giving their solutions to them. And then there's extra exercises that he's given as well.
Yeah, it's really good.
Yeah. Did you go through it, Christian, or?
Yep.
Cool. Yeah, I'm excited to leaf back through this. So.
Hey, before we get going, I wanted to mention I invited a friend of mine to come today, and Isaac, I wondered if you wanted to introduce yourself, and then Jake, if you could let him know how to get on the email list.
Oh yeah, for sure.
Yeah, sure. Hey guys. My name is Isaac. I've been studying math for like the last 12 years. In a PhD program at Kent State University in Ohio. I'm super excited about the RChain project, and basically just for the last month and a half, I've been trying to learn as much as I can about the ideas in this area, and just to see where I can kind of fit into the whole project. And so I'm just here to learn, basically.
Awesome. Welcome, as are we all. So yeah, great. Good to have you. I'll just send you a link right now, but so I just posted a link in the chat. So from that page, you should be able to hit that mailing list link and register for the Google group. And then that's, feel free to post anything to the discussion there, any questions or comments. And then that's also where the calendar invites for these go to.
Oh, cool. All right. Thank you.
Yeah. Awesome. Well, thank you everyone for coming. It's been a pleasure as always, and I look forward to talking to you next week. And then I'll follow up with you, Christian and Human, about figuring out content for future sessions.
All right. Thanks.
All right, thanks, Jake.
Thanks.
Thank you.
Thanks.
Bye.